So I'd like to commence. The title of our presentation today is Impact of Operational Parameters on dV by dt of silicon carbide MOSFET and a scheme for gate driver resistance selection to limit dV by dt. The motivation of the talk is silicon carbide, we understand, have a very high dV by dt, and which is a very desirable trait as it leads to reduction in switching loss, which results in an improvement in efficiency. However, high dV by dt also brings its own set of challenges. High dV by dt is known to cause reliability issues in many power electronic.
I think Aditya has lost connection. We'll check with him and let you know. Aditya, you're on mute.
Yeah, apologies for that technical glitch. Apparently, I lost my internet connection. I'm very sorry for that. Let me reshare my screen. Is it visible now, Divyanshi? Divyanshi, I request to respond. Is it visible?
Yes, it is visible.
Okay, thanks, great. So as I was stating, silicon carbide MOSFET are known to have high dV by dt, and this is a very desirable trait because it leads to reduction in switching loss and therefore an increase in efficiency. However, high dV by dt is also known to cause reliability challenges, and there are standards around the same to mitigate such challenges. Once a standard is NEMA standard, which state that the dV by dt for motor application should be limited to under 6 volt per nanosecond for induction motors. Now, what would happen if you go beyond this particular standard limited standards? It is expected that you will accelerate the degradation of the ball bearing, and you may accelerate the degradation of the winding insulation. So the bottom line is, in certain applications, you need to limit the dV by dt. So if you want to limit the dV by dt, one must understand the factors on which dV by dt is dependent on. So to discuss the same, shown here is a typical double pulse test circuit in which the bottom switch, which is the device in the test or the DOT, is undergoing a turn on transition. Now the turn on transition is shown here by this red curve over here. So this region is the Miller plateau region. Now, the rate at which this particular switch is turning on is dependent upon how fast the gate to source is getting charged up, right? And the gate to source charging is dependent upon what is the magnitude of the current which is being pumped into this particular gate node. So the gate current is will in turn be dependent upon what is the value of this resistance R, right? Now, we will come to understand that this value of Ig is going to be dependent upon the magnitude of IDS, which is the total channel current of the device, the junction temperature, that is Tj, and the drain to source voltage, which was applied to the device before it started turning on. So all of these three parameters are dynamic parameters and are subject to change during the operation of the device, right? So if you want to limit dV by dt to a specific desired value, we must understand the impact of all three parameters on dV by dt. So in our presentation today, we will be investigating the impact of all these three parameters on dV by dt. So first is the impact of IDS on dV by dt. So the diagram remains the same. This is still the DPT which we have, and the bottom switch is turning on. So as the gate to source voltage goes beyond this threshold voltage, the current through the channel of the device starts to rise, right? Now, as the current rises, the gate to source voltage also rises. Now, when the current has reached the maximum value, which is given by the inductor current, the gate to source voltage will get clamped to this Miller potential. आवाज नहीं आ रहा है?
Aditya, we can hear you. Go ahead, please.
Okay. The Miller voltage, so as I was saying, the current is increasing, and the current will increase to the maximum value, which is limited by IL. At this value, the gate to source voltage gets clamped to a potential which is known as the Miller potential. The Miller potential is given by this particular algebraic, which is obtained from device physics. Here Vm is the Miller potential, Vth is the threshold voltage, IDS is the channel current, and K is the device constant, which is proportional to the transconductance of the device. Now, during this region, there is still some potential difference between the driver and then the gate source voltage, and therefore the current is still being pumped in. But then, since this potential is fixed, this current gets diverted to CGD, and the CGD starts to discharge, resulting in the turn-on transition of the device, that is a device under test. Now, the total charge which is being supplied to this gate during this Miller plateau region is given as a Q transition, which is nothing but the area under the CGD versus BGD curve, right? And total charge divided by total time will give you the current value. So T transition here is the transition time. Now you have these two algebraic equation with you, and if you are going to manipulate this equation, you will end up with T transition is proportional to this particular quantity. And since T transition time is inversely proportional to this particular quantity, we can say that dV by dt will be proportional to this particular quantity. Now for a turn-on transition, VGG is going to be a positive quantity. And if you are going to see this, the dV by dt is proportional to under root of IDS value. So if you are going to increase the IDS value, VGG is a positive quantity, it is expected that dV by dt is going to fall. Now this is shown here diagrammatically as a fall in the dV by dt by this green curve. For the turn-off transition, VGG is going to be negative, let's say -5 in a particular case. And IDS value, if you are increasing, the dV by dt will increase in the negative sense, right? So you can say that the dV by dt is increasing if you are going to increase the IDS for the turn-off situation. So the deduction is that the turn-on dV by dt decreases with the increase in IDS value, and the turn-off dV by dt increases with the increase in IDS. Next is investigation of the impact of Tj and VDS on dV by dt. So the equation, governing equation remains the same. Here we have Vth, which is varying as the junction temperature is changing. So as the junction temperature changes, the Vth is going to change. The other quantities are fixed, that is IDS and VDS are fixed, right? So as the junction temperature changes, that is it's increasing, the Vth is expected to fall. And if Vth falls, the dV by dt is expected to increase. So for turn-on transition, the dV by dt is expected to increase and is shown here by this green curve. For the turn-off transition, the effect is going to be just opposite, and the dV by dt will be decreasing. For investigating the impact of VDS on dV by dt, we understand that CGD is inversely proportional to VDS. So higher the value of VDS, the CGD value is going to be lower, right? And therefore, the total charge which is being pumped into the discharge of CGD is going to decrease. Therefore, the transition time is going to decrease, and the dV by dt is therefore going to increase. So for both the turn-on as well as the turn-off transition, with the increase in VDS, the dV by dt is expected to increase. Now, we have investigated each of the impact of each of these parameters on dV by dt individually. To figure out what is the global maxima of dV by dt with the as each of these three parameters are varying, what we are doing is that we are trying to inspect the point where it would occur. So just by inspection, we can understand that the dV by dt is going to be maximum. The turn on dV by dt is going to be maximum at minimum current, maximum junction temperature, and maximum voltage. So this is going to give you an operating point at which the turn on dV by dt is going to be maximum. Similarly, by inspection, turn off dV by dt maximum point can be obtained. Now, once you have figured out maximum dV by dt operating point, the next task is to figure out the suitable resistance to limit the dV by dt to the desired value. So the first step in such a process is going to be determination of the value of K. Now, K is the same quantity which I had previously mentioned, is given by this algebraic equation. This can be figured out using this equation and the gate source voltage versus the gate charge curve, which is given in a typical data sheet. So here is the Miller plateau region during which the dV by dt transition happens. Now, in this particular curve, we can see that the curve is plotted for Tj is equals 25 degrees Celsius. So one can evaluate the threshold voltage at Tj is equals 25. VGS will be the mean value, which is obtained by taking a mean of this particular region, right? And IDS is the current which is given in this particular plot. So there is one equation, one unknown, and you can figure out what is the value of K. The next task would be figuring out the value of Q transition. The Q transition is nothing but the area under the CJD versus VGD curve, or which is nearly equal to VDS curve, which can be evaluated from the device data sheet, right? And the T transition time is the transition time based on the desired limit which you want to achieve. For, let's say, for 6 volt per nanosecond, what is the T transition time you are expecting, right? So T transition time is based on the user. So you have the value of Q transition from the device data sheet. You have that value of T transition from the user desired value. Next comes the value of R on and R off. So for determining the value of R on and R off, you need to determine the value of Vm, right? Because you have the value of Q transition and T transition. Therefore, you have the value of Ig, and you always have the value of VGG, like 15 volt or minus 5 volt, right? So the only quantity left here is Vm. Now this Vm can be evaluated from this particular equation. We have already evaluated the value of K. So other point here are known to you. That is, Vm for the turn on transition has to be evaluated at minimum IDS and maximum Tj. And for turn off, the operating point can be used to figure out the value of Vm. Now, if you have the value of Vm, you can figure out what is the value of Rg by plugging it in this particular equation. So once we had deduced how to figure out the value of Rg, that is for both the turn on and the turn off scenarios, we then developed a experimental setup to test our developed theory. So we have constructed here a double pulse test network. And we are varying the junction temperature of the device using a Peltier module. Right? So shown here is the experimental plot of the turn-on transition at 400 volt, 3.25 amperes, and 25 degrees Celsius. Now we ran this particular experiment for different devices under different conditions, and we will be discussing the same in subsequent slides. So first experimentation results discusses the impact of variation in IDS on dV by dt at fixed junction temperature of 25 degrees Celsius at a fixed voltage of 400 volts. We have considered two DUTs for this purpose. First is by ROHM and the second one is by volt speed. Both of them are rated for 600 volt. So we desire to limit the dV by dt to under 6 volt per nanosecond. And for the same, we have determined the value of R on and R off for both these devices. And we observe that the maximum dV by dt gets limited to under 6 volt per nanosecond. So basically, it is meeting our set criterion, right? And we also see that the nature of graph obtained experimentally is very similar to the graph we had analytically derived. So it is showing a good correspondence with our analysis. Next, we investigate the impact of drain to source voltage variation on dV by dt. We see that the dV by dt is increasing for both the DUTs as you increase the value of drain to source. And it is good correspondence with analysis. Finally, we investigate the impact of junction temperature variation on dV by dt at a current of 3.25 amperes and a drain to source voltage of 400 volt. We observe that for both the devices during during the turn-on transition, we see that the dV by dt is increasing, and for the turn-off transition, the dV by dt is increasing as was theoretically deduced. We also observe that for DUT1, the percentage variation in turn-on dV by dt and turn-off dV by dt is more than for DUT2. Now, this was expected because the threshold voltage variation in DUT1 is more as compared to DUT2 as per the data sheet. So this was kind of expected, and this is what we are observing here as well. So in this presentation, what we have done is that we have given a combined analysis of the combined impact of the operational parameters, that is the IDS, TJ, and VDS on dV by dt. We have then presented a scheme to figure out what is the resistance, what should be the value of the resistance to limit the dV by dt to a desired value. And finally, we have presented experimental results to validate our deduced analytical deductions. You can figure out more details of this particular presentation from this publication of ours. This was presented in EPEC 2024. Now, I like to pass on the mic to Mr. Nakamichi. He'll take on from this particular point. Over to you, Mr. Nakamichi. Thank you.
Thank you, Aditya. Can you hear me?
Yes, Mr. Nakamichi, I can hear you.
Okay. Good morning, everyone. Namaskar. My name is Madam Nakamichi at SanRex Japan. I'm a sales advisor. I know IIT Bombay is one of the highest universities in the world, so I'm very happy, proud, and honored to take this opportunity to do a webinar with you. And also, I'd like to say thank you for Mr. Sandeep Anando, Associate Professor, and Mr. Aditya Aman, who is a wonderful student of IIT Bombay. And also Ms. Divyanshi Patil, Associate Program Manager, who organized this webinar. I really appreciate for your kind support. And I'd like to introduce, sorry. Today, I'd like to introduce our silicon carbide MOSFET. So first, sorry, I think something wrong. Who is SanRex? I think you never had our company name. So let me tell you about our company. Sorry, I think something wrong on my presentation copy. So let me see. Okay. Okay. So now let me explain about our silicon carbide MOSFET. So now, who is SanRex? I think you never heard of a company named SanRex. We are manufacturer power supply, power semiconductor, and we have over 90 years history in Japan. And our headquarters is located in Osaka, Japan. And our annual sales about $220 million US. And we are listed in Tokyo Stock Exchange. And actually, our company name is Sunshine Electric Manufacturing Company Limited, and our brand name is SanRex. We have worldwide network. We have office New York, Finland, Singapore, Korea, Taiwan, and China. We have not office yet in India, but we have 2 employees in India now. One is Dhananjay Bashes. He is a sales manager. And another, we have engineer Bharat. They are working at their home in New Delhi. And I hope we are open new office in the near future in Bombay. Where the SanRex factory? This is a map of Japan. We are in a small island. Actually, India is 9 times larger than Japan. And I think you may know our capital of Japan, Tokyo. They are located in the state of Japan. And Osaka, third largest city in Japan. Our headquarters is located here in Osaka. And our semiconductor factory is called Okayama, western part of Japan. And there is a famous castle in Japan, a nice place here. So you can come to visit our factory in Okayama. And this is the picture of our factory in Okayama for power semiconductor. We have 4-inch, 5-inch wafer and manufacture diode, thyristor, triac, IGBT, and silicon carbide MOSFET. Next, let me tell SanRex silicon carbide MOSFET and history of SanRex silicon carbide MOSFET. I think you may know this brand name, Panasonic. They are one of the largest home appliance company in Japan. Actually, we are working with Panasonic for this silicon carbide MOSFET since 2015. This is a joint development. It's called DMOS technology, silicon carbide diode integrated MOSFET. Our target of application for silicon carbide MOSFET. We have 3 target applications for our silicon carbide MOSFET. One is industrial, like induction heating, high frequency power supply, and electric vehicle, like EV charger, and then railway or motor drive. Next lineup of SanRex SiC MOSFET. This is the lineup of silicon carbide MOSFET from SanRex. We have 100, 150 amp, 700 volt in the module. And actually, for example, 150 amp is rated current, but actually it's used by switching applications. So capacity should be double. So 150 means about 300 ampere capacity. Also, we have 50 amp, 700 volt in discrete package. In addition, we are now developing 300 amp, 1700 volt in the module, and 50 amp, 1700 volt in the discrete. They should be available in 2 months from now. The next advantage of SanRex silicon carbide MOSFET in the module. Advantage number 1, ultra low RD zone on resistance, even at high temperature because of DMOS technology. Look at this graph, junction temperature versus on resistance, RDS zone, company and SanRex. For example, SanRex silicon carbide MOSFET, even junction temperature 175 degrees C, our silicon carbide MOSFET RDS on is 35% lower than company A. So we achieved 4.5, only 4.5 milliohm at junction temperature 150 degrees C. And advantage number 2, built-in flyback diode. This is the market standard construction of silicon carbide MOSFET. So external flyback diode equipped. However, SanRex silicon carbide, because of this technology, DMOS technology by Panasonic, external diode is not required, but it's built in. So we achieved very compact package. Okay. Advantage number 3, high short circuit withstand time capability. Look at this photo. It shows short circuit withstand time capacity capability. Our silicon carbide MOSFET has only 8 microseconds. But as far as I know, market standard, other silicon carbide has only 3 or 4 microseconds. So our silicon carbide MOSFET has high durability. And next advantage number 4, compact low profile package. These are the structure of the module. Left side is conventional module package, and then right side is our new package. It's called Technoblock. Our new package, Technoblock, is 50% lower on height and 1/3 in volume. Very, very compact. Achieve lower inductance as well. And let me show you how compact this package is. And this is the market standard package, 62 mm package. And also this is major package in the market, 17 mm height package. And this is SanRex original package with 14 mm on height. It's called SanRex Technoblock. From side view, this is the market standard 62 mm package. This is market standard 17 mm height package. And SanRex Technoblock is this height, very low. And from top view, this is 17 mm package. This is 62 mm package. And SanRex Technoblock package, only this package size. You can know how small and compact SanRex Technoblock is. We achieve compact lower inductance as well. And next advantage number 5, durable performance on package. Let me show you the graph. This is delta TJ versus power cycle. Our power cycle in the Technoblock new package has 3 times higher versus conventional package on power cycle. So very, very high reliability. And next, let me tell you about the silicon carbide MOSFET advantage in the discrete package. Advantage number 1, high speed and low switching losses. Our package TO247 with 4 pin, so there is additional terminal, drain source, number 3 pin. Because of this, compared to 3 pin type, actually gate current and then drain current can be separated. Inductance also different. That's why loss is 90% lower compared to 3 pin type of TO247 package. Advantage number 2 for discrete, high current density. Our design is called clip-on design, but not wire-bond. That's why very, very high durability, reliability, because of high current density. Advantage number 3, isolate package of TO247. Our package isolate package TO247. So it's easy for mounting, for design. From now, let me tell you application example of SanRex silicon carbide MOSFET. First, motor drive. Customer located India. Our customer name HBL Power System. They are located in Hyderabad, India. This is the picture of the product. The application is 50 kilowatt PMSM drive. They use SanRex 150 amp 700 volt silicon carbide MOSFET module, 6 pieces inside. Because of very low, ultra low RDS on resistance, also very compact package, they can put our silicon carbide MOSFET module inside the motor. Next, solid state DC disconnector. This is also coming from India. Customer name is IIT Technology, Hyderabad. Professor Satish Naik. They are located Karnataka, India. These are the picture. And application is 800 volt bi-directional solid state DC disconnector. They use SanRex 50 amp 700 volt silicon carbide MOSFET in a discrete package, 2 pieces on this package, on this application. According to Professor Satish Naik, they already offer their product, this DC connector, to the company in the States, Boeing, for aircraft application. And next example, switchboard capacitor converter is coming from USA. Customer name, University of Dayton. They are located Dayton, Ohio, USA. This is the picture and diagram. The application is 500 kilowatt switch capacitor converter for EV truck and aircraft. They use 150 amp 1200 volt silicon carbide MOSFET module, 6 pieces on this package, on this unit. Next example, 4-leg SiC traction inverter. It's also coming from USA. The customer name, University of Kentucky. They are located in Lexington, Kentucky, USA. This is the picture and diagram. The application is 50 kilowatt multifunctional T-type 4-leg SiC traction inverter. They use SanRex 50 amp 700 volts silicon carbide MOSFET in the discrete 4 pieces in this application. The last one is wireless EV charger. It's coming from Thailand. Our customer name PanDrive, located Bangkok, Thailand. This is the picture of wireless EV charger. The application 5 kilowatt wireless EV charger. They use our 150 amp 700 volt silicon carbide MOSFET, 2 pieces per unit. They are upgrading to 7 kilowatt wireless EV charger now. So that is all I wanted to introduce our new silicon carbide MOSFET for you. I hope you enjoyed finding good performance of SanRex silicon carbide MOSFET. Finally, I'd like to extend our congratulations to your new Prime Minister, Narendra Modi. And I'm convincing India and Japan extension field to help each other to reach our goal. We work together. Thank you.
Thank you, Mr.
And I'm
Nakamichi, for that well wishes of yours and that.
Thank you, Aditya.
Yeah. We do hope to work along and reach new heights in days to come.
Thank you.
Yeah. So I see that there are few questions in the chat box. Okay, some of them are like, I'll start with the questions straight to your presentations. To Mr. Nakamichi, I'm reading from the chats. Silicon carbide MOSFET general trend is that on-state resistance shows positive temperature. Right? I think, Mr. Nakamichi, you would be the right person to answer this question.
Okay. Could you tell me again?
It would be appearing in your chat box.
Charge box.
Yeah, chat. So the question is, in slide number 2021, the on resistance
okay.
shows a negative temperature coefficient. The listener wants to understand why.
Okay. $22, no? Oh, the structure, right? The structure of the built-in feedback diode.
Yeah, on slide number 2021, the on resistance
21.
is showing. Yeah,
On
2021
resistance.
slide number.
Oh, okay. On resistance. Oh, okay. Chat. Page 19.
20.
Okay. Oh, okay. Yeah, 20. Okay.
On resistance is showing a negative temperature coefficient. The listener wants to understand why.
Negative temperature?
Yeah, negative temperature coefficient.
Junction temperature. Okay. Oh, okay. That let me ask an engineer.
Okay. Perhaps.
No.
Yeah, you may get back to this particular.
Yeah, sure. Yeah. Okay, I got it. Yeah.
And
why? Yeah. Are zone higher on the negative temperature, right?
yeah.
Okay. Let me ask the engineer. Sorry, I'm in sales, so there are no such questions in the past.
Okay. What generation technology is silicon carbide module and discrete? What generation technology? Like, is this your first generation of devices, or like have you rolled?
Yeah, actually,
previously?
for us, this is the first generation, and then now we are now upgrading and developing second generation chip.
Okay.
Yeah.
Yeah. So you are coming up with second generation as well.
That's right. In maybe a couple of years.
Okay. So I'll start with the questions which have been addressed to me. So yeah, the remaining questions I'll request Mr. Nakamichi to respond over mail, right? Which have been addressed to you. The remaining the questions which have been addressed to me, I'll try to respond. So I'll share my screen.
Okay.
Yeah, I hope my screen is visible to you.
Yeah.
Okay. So the question is, how are you ensuring that DPT boards gives the same result as that of actual converter where continuous switching is happening, since load parasitics will be different? Okay. So we recommend that you perform this test in the actual setup, right? So before you make the entire circuit operational, we recommend you to make the individual switches operate in DPT fashion. So that's the same policy we have been adopting in our lab. So and if you are doing the DPT testing on your actual setup, by default you will be incorporating the parasitics over there. So you can vary the IDS over the entire given range, and the TG over the entire given range, and the VDS over the entire given range, and then figure out what is the resistance which you would be requiring. So there you will be kind of addressing this parasitics effects as well. What is the bandwidth of the oscilloscope and the voltage probe for VDS measurement? Also, why the tests are done at low current of 3.25 amperes? Okay. So the bandwidth of the oscilloscope was 1 gigahertz. It was a Tektronix, Tektronix or by Lacroix, I don't remember. So the bandwidth was by 1 gigahertz. And the voltage probes for the gate voltage measurement, it was a passive probe rated for 1 gigahertz. For the voltage side, it was a differential probe, and it was rated for around 200 megahertz, if I remember well. Why the tests are done at low current of 3.25 amperes? We understood during our analysis that dV by dt turn on will be maximum at minimum current, right? And the turn off dV by dt will be maximum at maximum current, right? So we wanted to investigate what is the impact of low current on turn on dV by dt. So we took the value of current to be 3.25 amperes. And this test was done for a 30 ampere device. So this 3.25 was kind of 10% of the rated value. Also, we did the test at higher current for testing the turn off dV by dt. So you can find more details of the same in our publications which I had shown previously. As the Miller voltage is varying, as shown in slide 7, which VM need to be taken to calculate the gate resistance? So I'm hoping the listener is asking about the VGS versus the charge characteristic plot which was shown in the slides. So the listener is right in mentioning that the slope was having some slope, and you have to take the mean value of that Miller voltage, because you are interested in figuring out what is the mean dV by dt, right? Because the standards were on mean dV by dt. So you try to figure out what is the mean Miller voltage, and based on the same, you proceed with the calculations. So I think I have answered the queries which were on my part. The questions to Mr. Nakamichi, I think he will be able to respond once the technical team is back, and then maybe on a few days later. So that's
Sure.
there. Yeah.
Hello, Aditya. Hello, Aditya.
Yeah, sure. Please go ahead. Yeah, please go ahead.
Yeah, there are few questions at the bottom also. The chat is being updated. Can you just go through it if possible?
Okay. Slight ringing due to the rise time. What could be the reason? You're selecting. Okay, this is for me. If we are selecting the resistance to limit dV by dt based on IDS and TJ VDS, but this value will be highly variable. The load is dynamic. Won't it be the value of the resistance? It will change the value of resistance. No. So the entire idea is this value is going to be dynamic during the actual operation of the device. So you need to select the resistance such that you limit it under the worst operating case. So for as we had deduced, the worst operating case for turn on and turn off will be different. Like I had said that for turn on, it will be at minimum current, maximum TJ, and maximum VDS. So that is considering the dynamic condition. And yes, you are designing it for a dynamic scenario. So I think you will find, I'll request you to go through the paper. It will clear this particular doubt of yours. During fast switching with silicon carbide, dV by dt has slight ringing during rise time. What could be the reason? It is the common inductances, like common drain inductance and then the common source inductance, which is the cause of reasoning. So LdI by dt is there, and that is causing the ringing to appear across the drain to source. So this is there. How are you measuring dV by dt in the linear region of VDS waveform? So as per the standards, we are the standard state that you have to measure the dV by dt from 10% to 80% of the transition. So we followed the standard and we measured it from 10% to 90%. So 10% to 90% we measured the dV by dt. This question is to Mr. Nakamichi. what is the maximum device voltage of SanRex portfolio?
At the moment, 1200 volt, but we are now developing 1700 volt.
Okay, okay. So we can expect 1700 volt devices to roll out soon, right?
Yeah, in 2 months.
Okay, okay, that's great. That's great.
Yeah, we are targeting for the train application.
Okay. Share the slide. Thanks. Yeah. So I think we have answered most of the queries. We will get back to you and respond if any questions has been left unanswered. We'll respond to them individually over mail. So I'd like to thank all the listeners today for coming and attending our talk. It was great to have you all. I'll also like to extend my warm gratitude to Mr. Nakamichi for making time and coming over on a Saturday and helping us understand the devices which SanRex has, and his talk and his warm wishes for the Indian people. So thank you, Mr. Nakamichi. I wish you all the very well, and I would be. I'm hoping that our relation will just grow on from here on.
Sure. Thank you, Aditya, and everyone. Appreciate. Have a great afternoon.
Yeah, you too, Mr. Nakamichi. Thank you. Bye, everyone.